So tonight's talk is CDC and what can go wrong. You've got my name there, you've got my email address. As mentioned, we'll do questions at the end if possible, but sometimes you kind of think of one overnight or the next day. So there's my email address. You can send me an email, you can ask me a question, and I'll reply at some point, not necessarily instantly, but definitely I will reply. So CDC, what can go wrong? Or change data capture, WCGW, what can go wrong? That's another little acronym for you. So change data capture. So start kind of a little bit of an introduction to me. My name's Neil Stevenson, as my email address yet again. I am a principal architect at Hazelcast. You've probably heard of Hazelcast if you work with Java, or indeed if you work with other languages. This isn't really a talk about Hazelcast, and the CDC part is done by Debezium, but it's not really a talk about Debezium. But there's a demo and it's built around those two, so they're kind of going to be in there subliminally. So my kind of running time for tonight is I'm going to talk for about 35 minutes. I've got it just coming up for 5 past. So I'll talk till about 22 and then maybe 15 minutes of questions. Really, it's kind of a field stories pain I've had with CDC that if you don't have that pain because you learn from my mistakes, then that's a good thing. And you know, some of these are definitely mistakes and some of these are just kind of the way it works. So we have to start with a little bit of a definition of what change data capture is and a little bit of an explanation and kind of where it fits in the architecture toolbox. So this is the kind of idea of change data capture. You've got some sort of relational database, for example, and you do an insert into that database that creates a row in a table somewhere. And what happens is the database will write that into a redo log, an op log, a bin log, whatever you kind of want to call it, just a log file that records that change has been made to the database. So this is kind of originally part of the database internals. It's how they rebuild the database if somehow it gets mangled. And they also kind of use it for global replication if you've got kind of database where it's kind of appears to be in London and New York or wherever. That's kind of what it's for. So you do an insert. In this case, it's a table with 2 columns. ID column is 1 and the name column is Neil for obvious reasons. And then that creates there's an insert record in the redo log that says insert into table 1 with these columns, these fields for these columns. And then what you might then do is do an update because we decide we want to put my name in all capital letters. So we're now changing it to name equals Neil, where ID equals 1, and that changes the record in the database. And then that causes an update record into the redo log. And this is kind of the kind of key part to it, is that redo log is kind of a sequential series of what has happened. So it's not like, so the table itself, the data record changes, whereas the redo log is kind of like a history of what has happened. So there's an insert record, there's an update record, maybe there's a delete record. So you have to kind of play through them to find out what the actual kind of current positions is. And that's what they do when the database gets corrupted, which really isn't a thing you want to happen. So kind of conceptually, this redo log, it's an event store for change events, hence change data capture. It's capturing the change events being inserts, change events being updates, upserts potentially, deletes, but it doesn't bother capturing reads because reads aren't kind of relevant for that purpose. And there's some that consider that the redo log is the database, because that's the copy you rely on if the database gets deleted or the host it's on catches fire or whatever kind of bad thing happens. That's your restore point. So really that is the database in some views. And what you would see is the database, the table is kind of like the materialized view of the redo log, or maybe a cache, because it's a copy, a convenient copy that is more useful and easy to work with. That's maybe how I would define a cache. So if you're interested in that part, you can Google the likes of the Lambda architecture and the Kappa architecture, which kind of look upon this eventing as being the future, if you like, and what this is all about. I won't kind of cover them today because it's kind of more kind of side reading. But the part for today is that other tools can read this redo log. It's just a file. If we know what format it's in, we can read it and do something with it. So other tools might be, for the sake of argument, Hazelcast. So Hazelcast could read somehow that op log, that redo log, and store the same data in Hazelcast. And now our users might be accessing Hazelcast because Hazelcast is better. Or more convenient to them, or just whatever it suits them. So other tools can use that redo log, but it's kind of really important to understand that the redo log was never designed for that. This is just us bolting on extra functionality to solve a problem that wasn't a solution that was designed. So, one-way CDC. So this is kind of where we kind of normally start with CDC. You make this change with great imagination. I've called them System A and System B. We make a change to System A, it gets sent to System B, and System B has the same change. Eventual consistency, second later, System B's got the change. That's kind of great, really. That's what one-way CDC means. Is you're changing it in one system and the change flows in one direction to another system. So what's the problems with that? Well, problem 1A, or problem 1 if you like, there are going to be 5, so 1A, 1B. So 1A is this database redo log. It's typically kind of written after the database has changed. So you kind of make the change to the database row and then you write the redo log. It frequently happens that way around. Which means that System B cannot get the update until System A has had it. So there's a slight latency there. So briefly, System B is showing the previous value, maybe for a second or so. Does that kind of matter? Well, it might. So if you imagine the 2 examples I'm going to say today is you're doing a reserve and collect system for PlayStations, and you're doing hotel bookings, which essentially is reserve and collect. So if you've got PlayStations and your System B is showing the wrong number of PlayStations available, they're selling really rapidly. System A sells out, System B says there's some available. A customer turns up to collect their PlayStation and there aren't any. That is going to be disastrous because obviously you've lost that one person, and they're probably going to tweet about it and do all sorts of social media blasts that, I turned up and I was promised this and I didn't have it, and it's PlayStation, it's like gold dust. So it's kind of a bad thing. If it was a hotel, you turn up at your hotel and it's kind of overbooked or something. Well, I've had that actually happen to me. And all that happened is the hotel put me in a taxi to a better hotel and they paid the difference. So I was happy. So it's not necessarily a problem. But really all it kind of boils down to is it's not immediate consistency. It's not that the changes to the 2 are synchronized, it's asynchronous. System A updates, then System B. So problem 1B, which is kind of the same, is eventual consistency. Now, when I said, System A updates and then second later System B updates, that's kind of the usual flow, but it's not guaranteed. So the redo log is kind of written out, but, this redo log wasn't intended for CDC. So sometimes there's some sort of buffering for writing. So it might not be visible for you to be able to scrape that data from it for some period of time, an undefined period of time. Now, the war story I have was with Cassandra 3. I want to make it quite clear there's nothing wrong with Cassandra 3. It isn't doing anything wrong at all. It's just the way it's working. It wasn't designed for CDC. So in Cassandra 3, the file in question is called a commit log. So it writes it into memory and then flushes it down to disk. And it does it on a size basis. So the size of that log in memory is 1 megabyte. So you have to fill up a megabyte of changes before it writes it to the disk, before it is visible for you to scrape that data from it. So Cassandra 4 will do it on a size basis and on a time basis. So even if it's only half full, only half a megabyte of data, it'll write it out anyway after a set period of time. But with Cassandra 3, it's only when it's full up. So that is the part that really caused me a lot of grief. And once again, stress, Cassandra's doing the right thing. It's right now, it's up log in according with its configuration. We just would like to see it sooner because that would suit us. But that's not what it was designed for. But if you imagine your internal buffer is 1 megabyte and you're making half a megabyte of changes, then it's going to take 2 days for the changes to become visible. And probably that matters more. But if you're doing hotels, well, maybe it doesn't. You know, hotels will try and overbook because they know that people will later cancel. So that's how they kind of get to kind of nearly full. So several days may be the answer. And what I did for my example is because I didn't have a lot of data change, what I was doing, and it's kind of not wonderfully visible in the demo, but it is what's happening behind the scenes, is every time I do a change to Cassandra, I would actually change it 10 times. Just so that if I make a 1 megabyte change, if I've got 1 megabyte buffer, I make 100 kilobytes of change, I do it 10 times, I get a megabyte and out it comes. That's a really bad solution, but it works. So it's a good solution. I'm just not proud of it. It's just not the way to solve the problem. It's just kind of the best I could do. But it's a bad example because, you know, it means you get that the data has changed apparently 10 times and it hasn't really. I've just changed it 10 times to fill up the buffer. So if there was any trigger processing going on, that's going to fire 10 times. I would need idempotent handling of multiple updates. It's going to create a lot of change records that aren't necessary. It just isn't a good solution. It's just the best I could do with that version of the tool. Problem 2, or 1A, 1B, problem 2, we count from 0, maybe this is the third problem. Transactionality. So if you kind of take the idea that the redo log is written after the database is updated, then the database system E has committed its transaction. This redo log is essentially making the transaction visible. You know, that's over the right isolation boundary. Then system B gets that change to do the update. Well, what if system B doesn't like it because it violates a constraint or there's some reason why you would want to abort that transaction? Well, you can't because system A is already committed. So what do you do? Don't know, you decide. I mean, you can take the data, but if it violates your constraints, that then just messes up system B because it's got data that it shouldn't be allowed to have. If you don't take the data, then system A and system B deviate. So how does that get sorted out? Does that matter? Is that, well, obviously it matters if they're kind of deviating, but maybe it's not critical. Maybe you've got a solution. Really kind of the best I could come up with for this is just to be able to identify this deviation and somebody has to go and sort it out somehow. What that means kind of depends on the system in question, very much an application specific thing, no kind of general answer there. So that's one-way CDC, and that's kind of bad enough, really. It's a great tool. You just got to be aware of these problems. It's a way of keeping data updated because you're going to have lots of moving parts in a real IT system. You're going to have databases and all sorts of things, and you know, you might call them legacy because you kind of think of them as old, but they're doing what they need. You just kind of want that data somewhere else as well for integration. And this kind of leads us into the kind of two-way CDC. So now back to a diagram. We've got our system A, which makes an update. I'll change my names into capital letters. That flows to system B. Well, our users are connected to system B. They might change system B. So if you're changing the data in system A because you've got some overnight batch that updates system A, and you're changing the data in system B because that's what the live users are connected to, you've got CDC happening in both directions. So you might make a change to system A, which has to get to system B, and you might make a change to system B, which has to get to system A, because otherwise they'll never come into step. So that's what I mean by two-way CDC. You can change the data in either place. And it's not two-way CDC, it's one-way twice. So you've got a one-way CDC from system A to system B, and a one-way CDC from system B to system A. And what's important is that each of those one-ways doesn't know if the other one-way is present, because it's just unconnected. You're just kind of trying to join the dots and bolt things together in a way that kind of suits you, not, again, in a way that was necessarily designed for. Now this is where it really starts to kind of go wrong. And I'm sure you can kind of see problems. The biggest problem really is feedback. So you might make a change to a piece of data record in system A, sends it to system B. Well, that's an update to system B. The CDC system sees that as an update and sends it to system A. That's an update in system A. The CDC system sends it to system B, et cetera, et cetera, et cetera. As it goes round and round and round, your same data is changing. Change here, send it there, change there now because I've applied it, then it sends it to backwards, back round and round. And it's really kind of updates are the problem, because a delete isn't really a problem as much as an update. And now there's a create. Updates are really the kind of difficult one to handle, because if you try and delete a record that's already deleted, it's safe. And if you try and create a record that's already created, then that's a bit easier to handle. But really, we don't want those changes going around in circles, and we'd just like it if the CDC system sorted that for us and just said, don't do that. But the one I was using in my demo, which is Debezium, doesn't have enough information to do that. So I had to solve that problem. Now, if you're using a different CDC system, maybe it does, and you're laughing, you're away, you've got that one under control, but maybe not. So it's just a thing to be wary of. So how did I solve it? So I solved this problem with a thing I'm calling data provenance, or really it's change provenance. Where did the change originate? So if you've got a one-way CDC system, then it changes in system A and it goes to system B. Well, if you get it in system B, you know it can only have changed in system A, so it's implied. But in that kind of two-way setup, you can't kind of make that implication. So I was having a look, and if you're looking at JPA, it has kind of four kind of common attributes. It'll create on a data record, created by, created date, modified by, modified date. And if you have those data records on your data, then you can use that to filter your data in or filter your data out, depending on what you want, and kind of filter in, filter out. It's easy enough. Whoops. But there's a problem with this provenance. So there's a problem with those data fields that I've added. And in fact, in my example, I'm actually only using the last modified by. Who modified the data? I don't really care when it was modified, and I don't care when it was changed, when it was created. It was who changed it. That's the part I'm interested in for my CDC. And the problem is with who changed it, because it's just a field on the data. It needs to be set correctly. Now, I would arrogantly claim my code is always perfect, but in fact, as soon as you write tests, you realize your code isn't. But it's easier to think your own code is perfect. It just sits nicer. But can you obviously assume that somebody else's code won't be so good because then maybe they don't know about this, or they're just not very good. So it's at risk if that field isn't set correctly. And this is where the filter in, filter out side of things comes in. If you're filtering in or filtering out and you're not even setting it reliably, how is that going to work? So really, this isn't a good answer. it's a reasonable answer, but it relies on correctness and it relies on human correctness. It would be better if the system had a way of kind of figuring out where that data change occurred. And in some systems that exists, but not as a general purpose solution. So if you have to set that field, you set it reliably everywhere, it is kind of asking for trouble. It will be once, so you'll forget it somewhere. If the system does it, that's a lot better. Also, that makes the data record a bit bigger because that's a string field and there'll be a date field. And if you've got millions of data records, then that makes a data record look a bit bigger. Perhaps not catastrophic, but really the kind of better answer is if you can get something from the CDC implementation that you can kind of derive from. So for example, where you're connecting to system A, you might have a security principle, your logon password or some sort of token that tells you that was a user of system A and not user of system B. Or maybe you can kind of derive it from the driver. If JDBC driver, well, you must be connected to a JDBC system. Something, some piece of metadata is going to be reliable than user data. Problem 4. Problem 4 is, I don't really have a great answer for, is double update. So we're changing our data in 2 places. I was kind of saying, I might book hotel 1 in this system and somebody else books hotel 2. But what if we both book a room in hotel 1? How do we accommodate the fact that the same data record is changed in 2 places? Because you can't just say, well, take the oldest change or the newest change, or maybe you can. And you don't have transactionality, so you can't roll back and say, we'll abandon both. So how do we get to this eventual consistent state when we've done a deviating change? So it kind of depends. It's possible you could do some sort of merge. So if you imagine, say, for example, you were doing stock market trading, and you had an order, you wanted to buy 100 shares in company XYZ at £1,000. That's the kind of order detail. Well, you might change it, say, well, actually not 100 shares, let's make it 105 shares. And you might make that change on system A, and on system B, somebody else might make the change. Actually, let's not make it company XYZ, let's make it company DEF. Well, it's 2 separate fields in the data record, so you could kind of merge them together. But does that make any sense for a stock trade? Really kind of no, I don't think it does. If it was, that hotel booking and it's like there's a room booked for 1 night and I actually want to change it to 2 nights and I don't want the name to be Neil in lowercase, I want the name to be Neil in uppercase, well, that would be sensible. That would be allowable. So it kind of depends really. You can have merge logic, but it's application specific. So it's time for a bit of a demo. This kind of gets a little bit into the kind of weeds of Hazelcast and Debezium, but it's more of a kind of architectural view. So this is my system. I kind of wanted it to have lots of moving parts. So I've got a web client that is connected to my system. I'm not really going to show this today, but basically it's got 3 storage areas in Hazelcast. Hazelcast calls these maps. So it's like a Java util map, except it's spread across multiple machines. So it's got larger capacity. So that map may be connected to an external backing store. In this case, I've gone with Mongo, Cassandra, and MySQL, just for a mix of SQL and NoSQL. And a lot of Debezium relies on Kafka. Kafka is quite a kind of common messaging bus system, but that whole diagram is kind of the whole piece. If we look at it kind of a bit more in simpler view. So map A is connected to the Mongo database. So every time we change data in map A, we write it down to Mongo. Every time data is changed to Mongo, there's a reader process, which for Mongo sits elsewhere. It's not part of the Mongo node. It's on a different process. It reads data from Mongo, the change records from Mongo, injects them into a Kafka topic. that Kafka topic is something that Hazelcast can read from. It's got a Kafka connector. So there's the cycle for Mongo. So you can be changing data in Mongo somehow. The redo log reader reads it, injects it into a Kafka topic. Hazelcast reads it off the Kafka topic, and now it's in Hazelcast. You can change it in Hazelcast. It writes it down to Mongo, etc. So there's the loop for Mongo. So essentially, the kind of key point there is that the change data capture reader is a kind of separate entity. It's not kind of directly embedded in the process, because Mongo's clustered. You could run it across multiple machines. So which machine do you have the reader on? Cassandra, the reader actually sits on the Cassandra host, because the Cassandra oplog is just a file. So you're actually just doing a file watcher. So it's a similar idea. So you get you make a change to a map in Hazelcast, that writes it down to Cassandra. If Cassandra gets changed, there's the redo log reader, which posts that same change to the Kafka topic, and then it's the same idea as Mongo. You can read from, take data from Kafka straight into Hazelcast map. So that's kind of version 2. Well, and the last one is version 3, where Hazelcast can actually directly read from the redo log from MySQL, so you don't need the Kafka part for that. Over at the top left of my diagram, I've also got new data coming in on Kafka, just to kind of give me a data feed. Now, it kind of happens that this example is meant to be around a telecom system. So we've got tariffs, which are held in MySQL. We've got call records, which are held in Cassandra. And we've got customer records, which are held in Mongo. So every time a customer makes a call, there's a call record, and perhaps we would update the customer record with what their charge is based on the tariff. But I haven't bothered to implement that part. So time for a demo. And it's not the most visual thing for demoing. So I mentioned the kind of key thing was that this data is, most of it's flowing in and out on a Kafka topic, in fact, several Kafka topics. So I'm using a tool called CafDrop here, nothing to do with Hazelcast. So here is my calls topic. So this is the feed coming in from the outside world. This is actual customer events. And on my calls topic, I can see, so here's what a call looks like. Well, it's just a piece of JSON, you know, who was making the call, who did they call, how long did it last, and various other things. And here's my provenance fields. What created that job? What created that data record? What updated that data record? Well, because it's a creation, the created by and the modified by are the same, as is the timestamp. So that essentially is an insert. But the one that's kind of more interesting, kind of from a CDC basis, is if we look at the Cassandra change records. So if we change data in Hazelcast as a background process that's changing data in Cassandra, then what that creates is change records on Cassandra, which the oplog reader writes into this Kafka topic. I'll show you how Hazelcast reads it in a second. But basically, this is what we get on a Kafka topic for a change to a Cassandra data record. And the first thing to note is it's really big. You know, my Cassandra data record has got only like a dozen fields. And what the change record is showing us is here's the after position, because it was an update. The call successful field has the new value true. The caller's mast field, because it's cell phone, has this mast. The caller's callee's telephone number is this. So it just lists every field and what the new value is for each. So it's quite big in comparison to the size of the change record. So it's giving you a lot of metadata here. Has it been deleted? Has it been set? You know, it's a timestamp. And then there's various bits around, where does this come from? So the Debezium connector for Cassandra is what created it. And there's the actual file it read. There's the Cassandra commit log and various bits of other metadata. And if I go back And I try the same for Mongo. So I've also got the same job, in fact, is writing Mongo data, updating Mongo. And if I look at the Mongo messages, there we go. So what we have here is a similar but not the same thing, because data structure is different in Mongo, and I've got to scroll all the way down. So here is my new data, my after payload. So the first name field has the new value of James. Doesn't show me what it was before. It has the new last name field of Johnson. It has the new account type of standard int, etc. And if I scroll far enough, I'll see that that field was created by my preload legacy job, and somewhere it was modified by my preload legacy job. So that's an insert. If I scroll further down in my messages, then I would see that one of the ones towards the bottom has got a different update field. Quite a few in this. Let's see if we're lucky. So let's hope this shows. So they're all created by the same job, but was it updated by something different? Yes. So it was modified by a different job, my cleverly named update legacy job. So it was created by the preload legacy job and updated by that. So I now know that that isn't an insert, that's an update, and I know who's done that update because that field is set by my code. And if we look at the code itself, so I have got two parts here. We'll just do the Cassandra part. So this is the reader for Cassandra, Hazelcast code that's reading from the Kafka topic. So you give it the topic name, which is this. And basically, it's reading from Cassandra. It's passing through this validation stage, which I'm calling filter convert, and then it saves it into a map. There's a bit of Kafka properties just for connection. But the part that really matters, this is the magic, this is my kind of business logic, is I'm taking all these fields out of JSON, because JSON object, and I'm looking for the modified field. And if it contains the word update, so that update legacy, then I return a null. I basically drop that data record. Otherwise, I'll let the data record through. So this is me doing filtering based on the presence of that update field holding a certain value. So that is how data gets filtered on the way into Hazelcast, which breaks the loop for changes originating in Cassandra. The reverse is breaking the loop the other way. So this is the Hazelcast code that writes to Cassandra when data changes in Hazelcast, and it's doing the same thing. It's just looking, does that last modified field contain, is it churn update legacy? If it is, then you just log it and do nothing. And if it isn't, you do the save. So basically, that's the two parts of the chain. That if I see that code exists, then that field exists, then I will filter it out. I'll either filter it out as I'm loading it into Hazelcast or filtering it out as I'm saving it from Hazelcast. So that is it. Now, there's a kind of interesting side as well, is what happens around kind of schema changes. Well, because I'm passing everything about in JSON, I'm very tolerant of new fields being added to the schema because I'm just ignoring them. I'm just picking them out by name here. But that means if the schema changes, then how do you get that data in line? You need to make sure that both sides can accommodate the schema before you actually change the schema. So that's a little bit of an extra stuff. And just a last piece just to prove it. When I'm writing my data to Kafka, sorry, to Cassandra, I'm just looping through however time my loops is. In fact, it's only twice. It was originally 10 times, I think I did it. So just to kind of close off that's the code, that's the demo. It's not kind of wonderfully visual. Kind of the most important part really is to kind of grasp what these CDC records are. They've got a lot of stuff in them, a lot of data in there that you might use to do something with. So it's Debezium data JSON format. So just to kind of finish off then, this is what CDC record looked like from Cassandra. It's just a big blob of JSON. It's got an after field, and somewhere in that after field, there's last modified date, or more important was last modified by previous field, who's changed it. And there's a similar but not identical thing from Cassandra, where it's like, here's your CDC thing, and perhaps I could be doing the derivation based on the date. Maybe I know that the Hazelcast system is for kind of online updates, and users are only kind of in between 9 and 5, and the legacy update is an overnight batch. So perhaps the timestamp tells me it happens after 5 o'clock and before 9 a.m. Maybe I could do it time-wise. Would that be a better way? Don't know. So just before we go to kind of questions, just the kind of summary, the kind of 5 kind of things. Eventual consistency. It does not update system B immediately. You kind of need to know what it's likely to be, and maybe that's the average in the worst case. And your worst case might be open-ended. You would generally expect, we've all seen systems where, update it, log off, refresh the screen, whatever, and give it a few minutes, and it'll be fine. And usually it is, but sometimes it takes a long time. And if that long time is unbounded, then what do you do about it? Transactionality, well, you basically got to forget about transactionality, because you've committed a transaction, so you've committed a transaction. System B's just got to deal with it somehow. Feedback, that's that looping system, that's kind of disastrous. I've kind of solved it with Provenance. I really wouldn't say it's a great answer, but it's the best I could come up with, because if you don't have metadata that tells you enough to know where that change is originated, then it would go round in circles. So I think really the better answer is put in like a provenance check, and then some sort of catcher that kind of identifies if a data record same change appears more than once, because that would indicate it's gone round in a loop. Not really entirely sure how you would do that. That would would depend on your application. And double updates, changes can occur in both systems, then, it's just inevitable that changes will be to the same data record. So how do you detect those collisions, and how do you resolve them? 2 different questions. Detection is probably the more important part, because if you didn't detect them, you can't resolve them. But you don't necessarily have to do something. You might just say, it's all, we'll have to do some sort of database correction job to fix the data, rather than have the code figure out what to do, because maybe it's a very rare event. You generally wouldn't expect 2 people to be updating the same data record, but you might have a human updating a data record and a batch job doing it, and that's a bit more likely. But if you've got batch jobs, probably they're overnight. Okay, so that's me. Time for questions. Do we have questions in the chat window?
Yeah, we have just one.
Just one? Good.
Yeah, for now, maybe. Peter is asking, can you see the chat, Neil? Peter is asking,
let me just
what keeps the redo log from being a single point of failure?
Nothing, as far as I'm aware. You get, if your database system isn't clustered, then it's a single point of failure. So yeah, and that's the thing, that if it was clustered and you're kind of reading like a redo log, and then it crashes and it goes to the resilient copy, and then you start reading from the resilient copy, you might be reading change records that you've already read. You maybe got halfway through a log and now you're seeing them again. So you definitely have to be careful for recognizing that not only you might get the same data record twice. There might be jitter on the line. You might be me doing some stupid coding where I save it 10 times with the same value. So you definitely would want some sort of idempotent application process where you kind of maybe have a sequence number, or saying, we've seen update 55 to this data record. and we already have the correct target value, so we can safely ignore it. Maybe we kind of warn, we've got this record already, what's it happening? But yeah, so if your data record, if your system isn't resilient underneath and it has a hiccup and it's sending you that data a second time, then you have to deal with that. And that's problem number 6. There's probably 7, 8, 9, 10, lots of kind of stuff. And Debezium itself is very much a kind of, it's a new project. It's still evolving. I don't know if you saw, I was using like an alpha version of one of the modules there to get kind of support for the specific versions of the tools I was using.
Sure. Hey, Neil, this is Peter. How's it going? Thanks for your answer. And I just wanted to let you know that in Cassandra 4, which is imminently being released, there's going to be a proper change data capture feature based on Apache Pulsar. You can actually go to astra.datastacks.com, which is the managed databases as a service, and sign up for the alpha program for that today. And that, I think, should solve some of the hacks.
No, I'll take your first answer.
and workarounds. But just so you know, that is coming. It's gonna happen on a managed cloud service at first, but there is like a free tier that's fairly generous, so it's not like it's going to be closed source. Eventually, all this stuff gets open sourced back into Apache, Cassandra, and/or Pulsar. But yeah, there is going to be a proper CDC feature based on Pulsar, and like database change events will get published directly to Pulsar topics or queues.
Excellent. Yeah.
Yep.
Wonderful.
So just FYI, that's coming. Debezium's awesome, though.
I kind of picked Debezium because of kind of availability. It was like I was going to do I'll do MySQL, we'll do Postgres. Well, Debezium supports the board.
Totally. Yeah, exactly. Yeah. This thing is like Cassandra specific, and Debezium is a general purpose CDC tool. So
Well, I think that's where Debezium will need to evolve. It's a little brittle and rough around the edges because it's new and evolving, and it will kind of, I think, need to be a bit more specialized for each of the things it's trying to kind of do in a general, what it's trying to do in a general purpose way then gives me grief. And I hope, once again, I want to stress like Cassandra was just one that just totally threw me. I was where's my I thought I had this thing configured correctly, and I've done it all as documentation says, and then nothing came out. And then I can't remember, I left it running and I went for lunch or something, and I came back and it's worked. And it just took me, and it's blindingly obvious from the documentation, which when you know which bit to look at, it doesn't come out till it's this size. So I'm just interpreting that it was never designed for Debezium to look at, and that was just my kind of pain point.
I think you're probably right. So yeah, trying to address that in 4.0 for sure. Thanks. Great presentation, Neil.
Thank you.
Great. Thank you, Peter. Steve, we have more questions in the chat.
Yeah, somebody's asking, right, Neil Brown is asking, is this code on GitHub? Yes, it is. Hazelcast-platform-demos. So github.com/hazelcast/hazelcast-platform-demos. Or maybe you can type it into the chat window.
Yeah, go ahead. At least for the people here in the chat, they can get the address for the chat.
Yeah, there you go. Have I used anything other than Debezium? No, I haven't. But there's other kind of answers. I just kind of picked Debezium because it was kind of familiar territory for me in terms of the things it's connected to, because I've used these kind of systems before. And Kafka's a thing I'm kind of familiar with as well. So it was kind of, that looks exactly what I need kind of thing. It's very possible that there's other systems that are better. And it's very possible they're worse. I just haven't tried them.
There is Neil, there is a question that you skipped from Jay Kelly. He's asking if in your demo, were you filtering on way in or way out?
I was doing it both. But if I go to let me get my slide up because it makes it a little bit clearer down. Where is it? This one. And I need to share screen. So hang on, let me share screen. Okay, so I am filtering, if you can see my mouse, I don't know if that's visible on share screen or not.
Yeah.
So
yeah.
when MAPE writes to Mongo, there's a filter there. And this stage here between the Kafka topic and the map, there's a filter there. So the filter is in this place and the filter is in this place, but it's not here. So more data gets written to that Kafka topic than is needed. It would be nicer if the filter was there, but that would need the Debezium side to do it, and I couldn't figure out how to do that. Because basically what that means is you write a change to Mongo, it appears on that Kafka topic and you don't want it. Well, that's just wasting space on that Kafka topic. It's maybe not catastrophic, but it just kind of isn't something I wanted. So I'm doing the filter when Hazelcast reads in and when Hazelcast writes out, because I work for Hazelcast, I'm going to do it in Hazelcast. But that, I think, would be a better place to do the filtering out for changes that originate in Mongo. This is still the right place for the Hazelcast one. This is just our place that I did the other filter. So with all these things that you kind of say, well, what's maybe the rate at which it will be filtered out? Maybe you make 10,000 changes in Hazelcast and you've got like a batch job that makes 5 or 6 corrections. Well, having 5 or 6 out of 10,000 more than you need on the topic isn't really a big problem, but it's not really worth worrying about. But maybe it's 50-50, maybe half the changes on the topic are discarded, in which case it would be better not to get them onto the topic in the first place. But with it's just a implementation choice. But better to filter the earlier the possible, because there's going to be a time when somebody's doing something else with this data. They're reading it into another system or auditing it or something, and it sits on a disk and it gets backed up. And better places to do it, definitely. It's very much a pragmatic solution rather than a best in show. It works, but I'm quite happy to say it's not my finest work. It works, so in some senses it's meeting the requirements, but and this is a recorded call, so even then it's like, oh well, is that really the best? And it's like, it works. Sometimes you just kind of got to do it the wrong way to get it working. So more questions. I think we're meant to go on another 10 minutes. One new message.
Yeah, there is one more question from Neil Brown. He's asking if you ever tried any other CDC implementation libraries other than Debezium.
I haven't, no. But anybody else on the call care to chip in? I'm sure we're all kind of interested. It's the new tool in your toolbox, because you want, so historically what a lot of people have done with Hazelcast is they've had like some sort of relational database or whatever. And the business is growing and the database can't keep up. So you let's put this data in Hazelcast and we can access it a lot faster. And then, and ideally you change everything and it talks to Hazelcast, and then you've overcome your provenance problem because all your changes are now happening in the memory layer rather than whatever. But the reality is, for big systems, it takes a while to do those changes and you might never do them. So you're probably going to have changes in one system. And if you don't have CDC in the past, you just would have been doing some sort of polling. Maybe your Hazelcast information you clear out and reload every hour or every day or whatever. So if you load it every day, then it's wrong for half a day. Maybe you've got some sort of synchronization that, your batch updates happen overnight. And if you load your Hazelcast cluster at 6 in the morning, then it's got the right answer for the rest of that day because it won't change for another 12 hours. But there's definitely kind of better ways. You might go and do like a refresh on demand. Hazelcast has a mechanism where it can go and fetch a data record from a remote system on demand, but that's kind of not as fast as already having it in the first place. So that's kind of what that CDC does, is that keeps it fresh in the second copy, because the CDC is really just about joining things together that were never meant to be joined together.
Great.
Yeah, so somebody else has just posted, yeah, use Maxwell's daemon for CDC from MySQL. It's worked well. Connectors, yeah. Yeah, sounds good. I wasn't one I was aware of, so yeah, that's good. But MySQL certainly kind of a popular thing. Yeah, I mean, it just depends kind of what technologies you got in-house. Probably, you know, the Debezium kind of is that kind of general purpose thing. If you had one specific for one technology, then maybe it would be optimized and better for that reason. You know, that's just going to depend on what you're using.
Thank you very much, Neil. I think I'm not seeing any questions anymore. I'm going to share now here in the chat the YouTube channel for the Java community. It's the YouTube channel where the recording is going to be available in a couple of days. Okay, so you just watch this channel to see the recording and share and etc. And yeah, Steve, do you have anything else to say, to add? Looking just before you answer, I want to again thank you very much for sharing your knowledge, this important presentation, and of course for everybody who joined, who participated, and also asked questions, and even shared new information with you, right?
Yeah. So I might try that MySQL one. So that'll be good.
Okay, so I think that's all. So if we don't have any more questions, anything else, lots of thank you for you in the chat. Thank you, well done, Neil. And I think that's a wrap. Thank you, everyone.